बिस्मिल्लाहिर्रहमानिर्रहीम डियर स्टूडेंट्स, अगले लेक्चर के साथ हाजिर हैं और आज के लेक्चर में हम बेसिक सर्चिंग एल्गोरिथम्स को देखेंगे कि व्हाट बेसिक सर्चिंग एल्गोरिथम्स आर एंड वी विल एनालाइज द टाइम एंड स्पेस कम्प्लेक्सिटी ऑफ बोथ एंड वी विल कंपेयर द परफॉर्मेंस ऑफ बोथ। ठीक है ना, तो ये चीज़ हम इसको देखेंगे और बड़ी डिटेल से हम इनको डिस्कस करेंगे। तो पहले तो ये कि व्हाट इन फैक्ट सर्चिंग इज़। तो सर्चिंग इज़ द प्रोसेस ऑफ determining whether or not a value exists in a data set or in a data structure or a storage media or not. So we will discuss two searching methods on linear data structures. By linear data structures we mean arrays or linked list like that. ठीक है ना, तो there are two types of searching. First is linear search and second is binary search. linear search वो simple search का method है जो हम अमूमन यूज़ करते हैं और जो आपने पहले भी यूज़ किया है। ठीक है ना, द वन वी डिस्कस इन द लास्ट लेक्चर वाज इनफैक्ट लीनियर सर्च, जो एरे के अंदर किसी वैल्यू को सर्च करने के लिए इस्तेमाल होता था। तो यू हैव ऑलरेडी इम्प्लीमेंटेड इट, यू ऑलरेडी नो दैट। ठीक है ना, इट इज़ ऑल्सो नोन एज सीरियल और सीक्वेंशियल सर्च। वाई? बिकॉज इट सर्च फॉर एलिमेंट्स वन बाय वन इन सीक्वेंस फ्रॉम द लोअर index to the higher index. ठीक है ना, तो the linear or sequential search algorithm on array or any linear data structure, by array we mean any linear data structure, so it sequentially scans the array comparing each array item with the searched value. Let's say its key is the value to be searched. If a match is found, it returns the index of the matched element, otherwise it will return null. ये तो हम सिर्फ एल्गो के पॉइंट ऑफ व्यू से कह रहे हैं। तो इन अ लैंग्वेज जब आप इसको इम्प्लीमेंट करेंगे C++ में, तो आप कोई भी ऐसा इंडेक्स दे देंगे जो कि रेंज से आउट होगा और उसको चेक कर देंगे कि अगर फॉर एग्जांपल कोई नेगेटिव वैल्यू दे देंगे। आपको पता है C++ में नेगेटिव अलाउ नहीं है, तो अगर आप नेगेटिव दे देंगे तो उस पर आप चेक लगा देंगे इफ़ नेगेटिव वैल्यू इज़ रिटर्न देन इसका मतलब नॉट फाउंड या जो भी है उसको आप अपने तरीके से इम्प्लीमेंटेशन पॉइंट ऑफ व्यू से हैंडल कर लें। इन एल्गोरिथम्स वी आर नॉट कंसर्न्ड विद द एक्चुअल इम्प्लीमेंटेशन। ठीक है ना, नाउ दिस लीनियर सर्च कैन बी अप्लाइड टू बोथ सॉर्टेड एंड अनसॉर्टेड एरेज। नो व्हाई दिस पॉइंट इज मेंशन्ड हियर, तो ये आपको समझ आएगा जब आप बाइनरी सर्च में देखेंगे। बिकॉज इन बाइनरी सर्च देयर इज अ रिस्ट्रिक्शन ऑन इनपुट, दैट इनपुट मस्ट बी सॉर्टेड। ठीक है, तो इस वजह से ये एक एडवांटेज है लीनियर सर्च का। We step through array of records one at a time and we look for the record with matching key. Search stops when we find a record or when we have examined all the records and we don't succeed. ठीक है ना, तो अच्छा, आप एल्गो को लिखने के कई मेथड्स होते हैं, तो यहाँ हम मुख्तलिफ एल्गोरिथम्स में मुख्तलिफ मेथड्स आपको बताऊँगा ताकि आप किसी बुक के अंदर अगर कोई और मेथड देखें तो आप परेशान ना हो जाए। हमने तो इस अंदाज से एल्गोरिथम लिखे हैं। ठीक है, तो बाज़ दफ़ा स्टेप्स की फॉर्म में एल्गोस को लिखा जाता है। तो व्हाट हैपन्स इन लीनियर सर्च कि आपके पास इनपुट होता है एक एरे, मींस एनी लीनियर डेटा स्ट्रक्चर, अ लिस्ट जिसमें n एलिमेंट्स हैं जो भी हैं, एंड अ की इज़ द वैल्यू टू बी सर्च्ड। तो अब करते क्या है, सेट I to L, and while I is less or equal to the upper limit of this array, you have to do this comparison. And what is in this comparison? If current value of array at index I is equal to, in other way it matches, then go to step number 7. Step number 7 says element X is found at index number I, or in other words return I, and then it exits. If this condition is not satisfied in step number 3, it will continue to increment I and it will check again until the while condition is false. And if while condition becomes false, it means that we haven't found any key, means key was not found in the array, in the data set. So we will go to the next statement, which is print element not found, or in other words you can say return null, and then it will exit. So it is another way to write algorithms. The same algorithm can be written in a pseudocode like form. For example, this is the same procedure algorithm called linear search and input is the same. So what is the main functionality here, for each item in this list or in this array, if match item is equal to the value to be searched, or in other words you can say key, it is more appropriate to write key here in array. I will correct it in slides when I will upload it on LMS. And if match item is equal to the current value, or you can say key, return the item's location, and if otherwise it will return nothing. So nothing means null. So that is from implementation point of view. So it is another way to write the same algorithm. And if you want to write it in another form, which is more readable form, you can write it like this: algorithm linear search, where the input is an array which has index from lower to upper, and there is a key, that's the value to be searched. For I is equal to, from this lower to upper, what will you do? You will do a comparison, and if this comparison is successful, you will return the index for which the comparison was successful. Otherwise when loop will end, it means nothing found, so it will return null. ठीक है, तो इसकी सेम इम्प्लीमेंटेशन आपने खुद ही करनी है, क्योंकि दिस theoretical course, so implementation of all these algorithms it is in lab course. ठीक है ना. Now how will this algorithm work? For example, this is the list or array, whatever you consider it, and the key or the value to be searched is 33. So what will you do? You will first match this 33 with first one. It doesn't match, so it will go and check the next one, 14. There is also a mismatch here, and then it will compare it with 19, no, then 26, no, then 27, no, then 31, and then 33. Yes, it matches here, so it will return 7, because for instance we are supposing that the index is from 1 to 10, so it will return 7. If index is from 0 to 9, it will return 6, and if index is from -1 to something like that, to 8, so the index will be different. So for instance I have written that index is from 1 to 10, and if this is the index, then it will return 7. So search algorithm always return the index on which that value is found. So now we will do the analysis of this linear search. But whenever we talk about analysis, in fact we are talking about the space and time complexity, because these are the two major measures by which we can analyze the performance, the optimality, the optimization of an algorithm. So now see, first we will see the space complexity. You know, this is the array, and this is the input. So the size of array is considered as n, and this is the value which is to be served. This is also provided as input. So what other values do we require other than these two? So that is first this variable I, so it is used to control the loop, and this lower and upper limit come with this array, so no need an extra space for these. So we only need 1. So 1 means constant time. So space complexity of this algorithm is 1, so it is very optimal with respect to space, but we will see how much optimal it is with respect to time. So now see, whenever we're talking about time, see, if n is the size of the array, so the loop will run not more than n times. So the worst it will happen, that when it will search from lower to upper, it means it has traversed n elements. Either the key will be found or it will not be found. If it is found, it will return the last element if it is the last one, or it will return null if it is not found. So the maximum, the worst case, this loop cannot run more than n times, and when this loop runs n times, it does some comparison in its body. So total complexity will be n multiplied by this c, because this c, for example, c is the time taken to compare, or any constant time, it may be 1 or 2. So this constant work is been done n times, because loop run at most n time. So we're talking about the worst case complexity. So T of n will be equal to n into c, which is nothing other than order of n. So it runs in linear time. It's fast. So we cannot say that it is slow, but when we will compare it with a better algorithm, so with respect to that better algorithm, it will be very slow. So what that better algorithm is, we will study it later on. Now we will study its best case, worst case and average case. So in best case, what can be the best case? That the value that you are going to search is in fact the first value. So after first comparison, you get your result. So it means time complexity of best case is order of 1, means in the least time this algorithm can take to give you result is order of 1. It cannot take less than this time. And the worst case, there are two worst cases. One worst case is that the value that you are going to look is the last one. So it will compare all the values one by one, and after doing, if there are n elements, n comparisons. So for example, here there are 10 elements, so it means it will do 10 comparisons. So if these are n elements, so it will do n comparisons. So it will be order of n, and that we have already calculated here, order of n, the worst case. The second worst case is that the value you are looking is not in fact in this list. So in this case also you are going to check you are going to make same n comparisons, and after that n comparison you return null. So there is nothing change in it. So time complexity of this worst case will also be order of n. Now we will talk about what is the average case. We have already taught you what average case is. In average case, input, if input instance is concerned, so the value can be 1. The value to be searched can be at location 1, at location 2, at location 3. It can be at any location. It can be anywhere in the array. So average case time complexity is the average of time complexity of all possible input instances. So suppose we have an array of n records. So there is a possibility that you can find the value after one comparison, and there is also a possibility that you will find it after 2 comparisons, and the same probability is for all, that it is the same probability that you can find the value after 3 comparisons, and it is the same after for 4. So all these events are you can say likely to occur. So it means there is no disuniformation, or there is no biasness in this. So every event can occur with the same probability. So if this is the case and we have n records, so if we search for the first record, then it requires 1 comparison. If we search for second record, it requires 2 comparisons. For third it requires 3. For 4 it requires 4, and for n it requires n. So the average case of all these searches is 1 plus 2 plus 3 up to n, divided by n, because there are total n cases. So if we solve this, the sum from 1 to n is nothing other than n into n plus 1 divided by 2, and you are dividing it by n. So 1 n will be cancelled above and below. So it will the result will be n plus 1 divided by 2, which is nothing other than order of n. So it is in fact linear time. Average case is also linear time. Now what are the advantages of this linear search? You see, it is very simple. You have done it without knowing that it has such algorithm. So it is easier to understand and implement, and it doesn't require the data to be sorted in any particular order. This is a very big advantage. But it has also some disadvantage. What is the disadvantage? Is very poor efficiency, as it takes lot of comparisons to find particular record in big files, especially when your data is at the end of these records. So whenever we have got a very large database and we require speed, especially in real-time systems, so it will be very time consuming, and it literally fails in these conditions. So it fails in very large databases, especially in real-time systems where we are very much concerned about time. So we are not concerned about space too much, so we are concerned about time. So to have a better algorithm, let's study these three scenarios. Suppose you are searching for a person in a phone book. So it's a very old type of example, but let's consider it. And the person whom you are searching, his or her name starts with, for example, K, and you know that K is in between, about in the middle from A to Z. So you can start searching at the beginning and keep on flipping all the pages with titled A, then B, then C, until you get to the pages that are titled with Ks. But in fact, it will be a better approach, and you will most likely you will follow this, that you will start from mid and you will search for K, and you will start searching from K, because you know that K is about in the middle. So you will not try to search from A. You will your first need will be that you reach as fast as possible to this K. So you will try to open the book from the middle, and then approaching to K will be easy. So there is a similar scenario number 2. You are searching a word in a dictionary and it starts with O. So what you do, you start searching it or flipping pages from A. So it will take lot of time. That is in fact linear search. And there is another method which is very efficient one, that you start from middle. So it will be around M, N, O or something like that, and you will approach O more quickly in fact. So it is most probable that you will start near the middle. There is another similar scenario, that you log into Facebook, and when you do, Facebook has to verify that you have a valid account or not. So it needs to search for your username in its database. Every time you log in, it does the same process. So let's your name is Larab, for instance. So Facebook should start starting from A's and search for your name. It will take a lot of time, because there are about 2.7 billion monthly active users of Facebook. So if it will do about, if your name is in the middle, so let's say it will do about 1.3 or 1.4 billion comparisons. So you can think how much time it will take. So it makes more sense for it to begin somewhere in the middle. So your search can be more efficient, and this is what this is the methodology that is used in binary search. And in all these cases, we have used the algorithm which is called as binary search. We start searching from the middle, and that makes search very easy. So binary search is a searching algorithm, and but there is a limitation that its input is a sorted list of elements. Your input must be sorted, just like in dictionary everything is sorted, and just like in index tables everything is sorted with respect to that index, and just like in your diary, for example, the dates are in a sorted order. So if an element you're looking for is in that list, binary search will result its position where mean the index where it is located very efficiently. Otherwise, if it is not found, it will return null. So basic output is the same, but the working mechanism and its performance is different from that of sequential search. Now we will compare it with the linear search, and we will study an example. So suppose I am thinking of a number, and I say you that the number is between 1 and 100, and I asked you to guess that number. Now you have to try to guess my number in the fewest tries as possible. So with every guess, I will tell you that if your guess is low or high or correct. So for example, what happens in linear search, you start from beginning, and you start guessing like this, just from beginning, 1, 2, 3, 4, and you say 1, I say no, it is too low, and you say okay, it is 2, no, it is too low, and 3, it is too low. This is called sequential search. So it is very poor form of searching. So with each guess you are eliminating just one number. and if my number was 99 or let's say 100, so it would take you 99 or 100 guesses to get there. So if in a Facebook, if I have a Facebook account and my number in the list of that Facebook database is 2.4 billionth, then it will take with linear search 2.4 billion comparisons, and it will take a lot of time, believe me. Now here is a better technique. Start with 50. Now so you say my guess is 50, and if I say it is too low, then it means from 1 to 50 all number are too low. So your number does not lie between 1 to 50, it lies between 51 to 100. So you just eliminated half of the numbers in just one go. Now you know that 1 to 50 are all too low. So for example, your next question is 75, and I tell you that it is too high. So again you have cut down the half of the remaining numbers, about 25. So with binary search, you guess the middle number and check it. In this way you are eliminating half of the remaining numbers every time in every iteration. So for example, I say next is 63, your guess, which is in about the halfway between 50 and 75. We always consider integer values, so it may be a ceiling or a floor function. It may be 62.5, maybe 63 or 62. It is no problem. It depends on what logic you are using. And I say too high, and then you say okay, if it is 57, and ultimately you will reach it with fewer iterations. So this is in fact binary search. So here is how many numbers you can eliminate every time. For example, at most, if I have guessed any number from 1 to 100, so at first go you can eliminate 50, on the second go you can eliminate 25 more, and on the third go you can eliminate 13 more, and on the next iteration after you can eliminate 7 more, and then 4 more, and 2 more, and then there will be just one left. So either it will be your number, or a number will not be in this list from 1 to 100. I have guessed another number. So maximum 1, 2, 3, 4, 5, 6, 7. So maximum about 7 or 8 steps are required to find that number out of these 100. So there is a huge difference, because sequential search needed about 100 comparison. It needs only 7 to 8 comparisons at most. So that is the advantage. So whatever number I am thinking of, you can guess in a maximum of 7 to 8 guesses, because you are eliminating so many numbers with every guess. In linear search, you were eliminating just one at a time. So it was not a good approach. Now suppose you are looking for a word in the dictionary, and dictionary has 240,000 words. So in the worst case, how many steps do you think each search will take? Simple search could take 240,000 steps if the word you are looking for in the worst case is the very last one in the book. But with each step of binary search, you can cut the number of words half until you are left with only one word. So maximum how many steps? 18 to 19, because firstly you will have 240,000, and if you guess the middle one, then you will eliminate the half. So it will be 120k, then 60k, then 30k, then 50k, then 7.5. Then you see from 18 to 19 steps you can get your result. So just compare 240,000 comparisons in linear search and just 18 to 19 comparisons in binary search. A huge difference. It will make a difference of months and years if n is very, very large. Now we will see how it works. Suppose we are going to search 31 from this list. So you will find the middle value. So 9 plus 0 is 9, and if you divide it by 2, it becomes 4.5. So you can either take 5 or you can take 4 as the middle one. So suppose I am taking 4 as the middle value, that is 27. Now I will compare this 27 with this key. So I know that my key is greater than this 27, so it means it doesn't lie in this half of the section. So all of this I have colored it black, so it means that we will not consider it. So we are not going to make guesses for 1, 2, 3, 4, 5 elements. Just one guess was sufficient to eliminate these five possibilities. Now what is left? Now lower limit will be now mid plus 1, means my mid was 4, so lower limit will become now 5, mid plus 1, and I have to now search it from 5 to 9. Now what will be the midpoint? 5 plus 9, but it will be 14. 14 divided by 2, it is 7, so my mid will be 35. Now I have to compare the the value at index 7 in this case with key. So my value is in fact less than this value, so it means I will not consider these values. So I am eliminating 3 more values. So this was mid and upper limit was 9, so my upper limit will now become mid minus 1. So my lower limit is 5 and my upper limit is now mid minus 1. So I am going to add these 5 plus 6 and I will divide it by 2, so it is 11 divided by 2, 5.5. So suppose I will take 5 as mid and I will compare it with key, it matches, so I have found it, so it will return this 5. So this is how it works. So here is the algorithm, a very simple one. So it has 2 versions, one is iterative version and the other one is recursive version. So first of all I will teach you what the iterative version is. In iterative version we are going to use loops, and in recursive version we are going to use recursive calls. So algorithm is binary search, and what is the input array and a value key to be searched, and lower and upper bounds are already decided. While what will you do? While L is less than equal to U, means until or unless this lower bound becomes the more than this upper bound. You see, I will explain this to you. You see, first of all, there was a list of 10 elements, and then when I discarded 5 elements, my list was of just these 5 elements, which are white now, and then I halved it. It contained just 2 elements, and if the value to be searched was not 31, for example, it was for example 33 or 34, so it means I have to halve this one again. So what I was going to do, that I was going to split this one too, 31 and 33. So I will discard 31 because my value was not 31, and I will just consider this one. So in this case, this list contain of only one element. This will be the lower one, this will be the middle one, and this will be the upper one. So it is the lowest level. If the value to be searched was 34, for example, so value isn't found. So what will you do? You will change this middle and upper and lower values. You know what was happening here, that this 4 was the middle value. When I eliminate and this was lower limit, this was the upper limit, and this was the middle one. Now when I discarded all these, this value became the lower one, and this value remained upper one. I didn't alter it, and 35 became the middle element. So the previous middle, I added 1 to it to get this L. So sometimes I am going to add 1 to this middle one to get the next lower limit. So it happens sometime. And for example, if I reach here, this is the lower limit and this is the upper limit. And what I'm going to do is that if I'm going to discard it, suppose value to be searched is 33 or 34, I'm going to discard it. So I'm going to, in fact, this is also the middle one. So I'm going to add 1 to middle one to get the next lower bound. So now L and U are the same, but after this step, when I will increase the value, because if there is only one element in the list, so this is the upper bound, this is the lower bound, this is the middle value, and after this iteration his value is not found, what I will do, I will assign either 1 plus this middle value to lower one, so this L will go shift to here, so L will be greater than this upper bound. So it means there is in fact nothing, there are 0 elements now, and this process, this recursion or this iteration process must stop here. So that is in fact the condition if L is less than equal to U. So lower bound has to be less than equal to this upper bound, equal to if there is only one element. So if there is one element, the same index is in fact the lower and the upper one. But if there is no element, so then lower or upper bound will not be same, then lower bound will be one more than the upper bound, or in the other words upper bound will be one less than the lower bound. You will get to know this when you will simulate it. You will run it, you will run this algorithm on a paper, then you will come to know that how this condition works. So this is in fact an assignment for you, not a graded assignment, it is an ungraded assignment, but it will give you a more clear idea of this condition. So what you are going to do, you are going to find mid. How can you find mid? You add lower and upper indices and you divide it by 2, and then for example value is 4.5, so you can consider 4 and 5, it depends on what function you are using. I am using floor function, so I will consider 4. If you want, you can consider the ceiling function, so it will not make any difference. You can consider 5. So it is not any, it will not make any difference because we are only meant to have integer values here. So if this value at middle is equal to key, you are just going to return that index. But if it is less than, you are going to add 1 to mid and make it the lower bound, and I have already demonstrated it in the previous example. See, and otherwise you are going to subtract 1 from mid, and this value will be now your upper bound, and in the previous example both these cases have been discussed. So you can see the previous example, this one, in this one both these cases has been discussed. And if this loop ends and L becomes greater than U, means there is nothing to search now. So it means if this loop ends and there is nothing to search more, there are no more values, so you haven't found it, so you will return null. So the same approach applies to the recursive version. What you do, you say if L is greater than U, means lower bound, if lower bound is greater than upper bound, it means there is nothing to be searched, so you will return null. Otherwise you will do all this work, and this work is the same. You will calculate mid, if it is equal to key you will return it, if it is less than key, so you will consider mid plus 1 as lower bound, and you will call this function again. Otherwise if it is greater, so you will consider mid minus 1 as the upper bound, and you will call that function again. So working is the same, you will see it side by side. Return null condition, so it will be executed when L becomes greater than U, so that is what we have done here. Otherwise it will do this work, and this same work is done here. Here iterations are controlled by while loop, and here iterations are controlled by this binary search, because this binary search algorithm is calling this binary search algorithm. So it is the same that you are doing it with a while loop. So power wise both are same. What you are doing here, that L is equal to mid plus 1. So here you are also doing that. But upper limit is unchanged and lower limit is in fact mid plus 1. So it is same. Here with this new lower limit, you will repeat this whole body. So what you are doing here with this new lower limit, you are calling this function again. It means you are going to repeat it all. So it is in fact same. Recursions and iterations, or in other words loops, are considered of same power. So now we will calculate the space complexity of both the algorithms. Space wise both are different, but time wise both are equal. So space wise, what is the space complexity of the first algorithm? If size of array is n, then you just need one for mid and nothing more. no more. So you need just only one extra space, so it is order of 1. But as far as space complexity of the recursive version is concerned, it is order of log n to the base 2. Now how it is, we will prove it. Here is the algorithm, the recursive version. Suppose we are calling A32, there are 32 elements, so in the first recursive call, it will do some comparisons. Suppose it takes time c, and it will call the function again with about 16 elements. So because it has eliminated 16 at the first half, it eliminates the half. So half of 32 is 16, so it will call a of 16. And in the next step, a of 8 will be called. In the next step, a of 4 will be called, and there are some comparison which will take some constant time c. So we've got no problem with it. And then a of 2 will be called, and half of 2 is 1. So half of 1 is not in fact 0. So what happens when it is a of 1? It does all the same work and it calls a of 0, because we are calling it with a ceiling function. It is not actually the half, it is calling a of 0. And when it is a of 0, it is doing nothing but just this one comparison. So let's say it is also c. So this is all work which has been done, and you know the depth of the tree determines not in fact the actual nodes. So if there were more nodes, so we have no problem with that, but the depth of the tree determines how much height of stack we need. So for a of 0 we have got just one call, for a of 1 we have got 2 calls, and for a of if n is equal to 2, then we have got 3 calls, and if n is equal to 4 we have got 4 calls, and if n becomes 8 we have got 5 calls, if n is 16 we have got 6 calls, and if n is 32 we have got 7 calls. So for n we may have some x calls. So what in fact this x is, you can write it as this. So there is a common pattern between all these values other than a of 0. So a of 1 is in fact 2, a of 2 is 3, a of 4 is 4, a of 8 is 5, a of 16 is 6, a of 32 is 7. So this 2 is nothing other than log of this 1 to the base 2 plus 2, and this 3 is nothing other than log of this 2 to the base 2 plus 2, and this 4 is nothing but log of this 4 to the base 2 plus 2. So we can have a formula other than this one, log of n to the base 2 plus 2. So this x calls are in fact log of n to the base 2 plus 2 calls. So if the function is called with any parameter n, so there are in fact log of n to the base 2 plus 2 function calls. So it means this tree has such many levels, so you have you must have a stack which has such many levels too. So if each block of this stack consists of some k memory location, then total space required will be k into log of n to the base 2 plus 2, which is nothing other than, you can say, order of log of n to the base 2. So it space wise it is a bit you can say its cost is more, because binaries in linear search cost was order of 1. It was a constant cost, but now it is logarithmic cost. So logarithmic cost is always greater than a constant cost. But when we compare their time complexities, so time complexity of binary search is much faster than that of linear search. And in modern day systems we are mostly concerned with time. We are not concerned with space so much, because order of log of n to the base 2 is not that space that we cannot manage. It is not a high space. It's logarithmic space is also considered as a very efficient one, not with respect to a constant one, but still an efficient one. So we are in real time systems, we are concerned with time. We have to get our result as soon as possible. So can you imagine logging to your Facebook or Gmail account after 2 minutes, after 3 minutes, after 4 minutes? So you will leave it at once. So we are concerned with time in fact. So we will now see what is the time complexity of this function. So time complexity of both is iterative and recursive is same because the functionality of both is same. These are of equal power with respect to time. So I'm going to calculate the time complexity function of only one algorithm, and that is which version? It is recursive version. So you see, when I'm going to call t of n, it is calculating mid, it is doing some comparisons here. So for example, it takes some constant time c, and then it is going to call this function again either here or here, and what will happen it will call this function with about half of the elements that were called previously. So it will be n by 2. We are using ceiling function, and when we are going to call it with t of 1, it is also doing some work and will it call t of 0, and when I will call t of 0, it will do this one comparison and return null. So suppose it also takes some constant time c, so I can ignore this because 4.5 or 4 is it makes no difference. So this in fact ceiling makes difference of about just 0.5, so we can ignore it. We can write it like this. Now we are going to solve this equation by it is a recursive equation, so we are going to solve it by all three methods. So first I will solve it by back substitution method. So you know that t of n is equal to t of n divided by 2 plus c, and t of 1 is equal to t of 0 plus c, and t of 0 is c, and this is in fact the anchor condition. So what you are going to do, you are going to find the value of the next iteration. So if I place n by 2 in place of this n in this equation 1, I will get this equation t of n divided by 2 square plus c, and if I put the next iteration in it, means I substitute n by n divided by 2 square, then I get t of n divided by 2 cube plus c. Now if I get these three equations and I substitute equation 2 in equation 1, and I get equation 4, and then I substitute equation 3 in equation 4, and I will get equation number 5. So what happens here, t of n is equal to t of n divided by 2 plus c, and this t of n divided by 2 we can get it from equation number 2. This is t of n divided by 2 square plus c. We put it here and we get this value as equation number 4. Now what we are going to do, we are going to substitute this t of n divided by 2 square, and we will get this value from equation number 3. We will put t of n divided by 2 cube plus c in place of this t of n divided by 2 square, and we will get this equation. Now suppose we reach t of 1 after some k calls. So if this 3 is k, so this number is in fact the constant multiplied by this c. So if it is 3, it is 3, if it is 2, it is 2, if it is if power of 2 is 1, it is 1, the coefficient. So if this power is k, though the coefficient will be k. Now for what value of t of n divided by 2k, so what value of k, t of n divided by 2 will become 1. So we know that 2 of n divided by 2k is in fact 1. So n is equal to 2k, you can write it as like that. And we have done previously in the lectures that n divided by 2k means that k is equal to log of n to the base 2. So equation this 5, if I consider this one and I put n divided by 2k, we know it is equal to 1, and t of 1 is equal to t of 0 plus c, we already know that. So it is in fact t of 0 is c, so c plus 2k, so it becomes 2c plus c, and we know the value of k is log of n to the base 2, and we put value of k here. So this is constant, we can eliminate it. This is constant c, we can neglect it. So what will be left? Or log of n to the base 2. So what is the time complexity of the worst case of or the average case of binary search is log of n to the base 2. Now we will also do it by recursion tree method. So process is the same as we have discussed earlier. So there as the value of a is 1, so there will be only one branch at each step. So we will decrease the input side by a factor of 2. It means we will divide the input by 2, and after each splitting, not splitting you can say, after each branching, total work c will be done. So here what happens when we will call a of n, it will call a of n divided by 2 and there will be some work C. N of 2 will be called n divided by 2 square and we will do some work, some comparisons and assignments and arithmetic operations. So it will have some constant time. And similarly this process will continue until we reach to t of 1. So we know t of 1 can be further expanded to t of 0 and it will do some work C, and t of 0 means C. So how much these C, total work is in fact this C. So if we add all these C's, so how much are these C's? So you see how much levels are these. So if this is 2 power 1, so from 1 to k there are k levels. So there is one level above it and one level below it. So these are only k plus 2. This is the same thing we have done before. So in fact these are k plus 2 levels, and on every level work done is C. So total work is in fact k plus 2 into C. What is the value of k? If n divided by 2k is equal to 1, so it will be equal to value of k will be equal to log of n to the base 2. So if we put this value, so if we simplify it, it will become order of log of n to the base 2. Now the same can be done by master theorem, so result will not change. We have this equation t of n divided by 2 plus c for n is greater than 1. So you see here coefficient with t is 1, so a is equal to 1, b is equal to 2, there is nothing like n power something, so c is 0, and there is nothing like log power something, so d is also 0. So these are all valid numbers, so constants are fulfilled. Now I have to compare a with b power c. So b power c means 2 power 0 is 1 and a is already 1, so a is equal to b power c. So I will go for this second possibility, the second group, and in this group I will look for the value of d. If value of d is 0, then d is greater than minus 1. So I will put value of a, b and c and d in this formula, and if I put this value here, so this is what I get. So log of 2 to the base 1 is in fact 0 if you calculate it, and 0 plus 1 is 1, so n power 0 is nothing but 1. So I get big theta of log of n, and that is the same result that we got from back substitution method or recursion tree method. Don't get bothered about from this big theta symbol. You can write big O in place of it. It will not be considered as an error. So the result is verified by all the three methods. Now here are some practice questions. Suppose you have a sorted list of 128 names and you are searching through it using binary search. So what is the maximum number of steps it would take? So you have to calculate it by yourself. It's very simple answer. And suppose you double the size of the list. The size of the list is not 128, it is double of 128. It is about 256. So what is the maximum number of steps to find any value using binary search now? So you have to answer both these questions. Very simple questions. Anyone can answer who have studied this lecture. Anyone can answer that. And we have already taken this quiz. So that was all from today's lecture. तो उम्मीद है कुछ आपको समझ में आया होगा. जहाँ आपको कुछ समझ ना आए तो आप फ़ौरन मुझे ग्रुप के ऊपर क्वेश्चन पोस्ट करें. मैं इंशाअल्लाह उसी वक्त उसका रिप्लाई कर दूंगा, या मैं अगले लेक्चर के अंदर उस पॉइंट को क्लियर कर दूंगा ताकि सबको किसी किस्म की एम्बिग्विटी ना रहे. ठीक है ना. तो बाज़ दफ़ा लेक्चर्स के अंदर कुछ चीज़ें छोड़ी जाती हैं जानबूझ के, ताकि स्टूडेंट खुद उसकी ब्रेनस्टॉर्मिंग हो सके, वो खुद थोड़ा सा चीज़ों को देख सके. प्लेट में हलवा बना के देना नहीं होता बच्चों को. ये यूनिवर्सिटी का लेवल है, इसमें कुछ काम और एक्टिविटी बच्चे से करवानी पड़ती है. ठीक है ना. तो इस चीज़ का आप लोग ख्याल रखें. ठीक है ना. तो यू हैव टू डू दिस वर्क बाय योर सेल्फ. अगर कुछ चीज़ें आपको नहीं आ रही हैं, हाँ उसके बावजूद अगर आपको क्लियर नहीं हो रही हैं तो आई एम हेयर, इट्स माई रिस्पॉन्सिबिलिटी. तो मैं उसको इंशाल्लाह ताला क्लियर किए बगैर आगे नहीं जाऊँगा इंशाल्लाह ताला. तो ख्याल रखिएगा जी. अस्सलाम वालेकुम.